Watching football is one of America's greatest pastimes. I personally enjoy waking up on a Sunday morning to have a day filled with football. As I sit in amazement at the physically elite players making incredible plays, I often find myself wondering about stat lines and records in the NFL. Surprisingly, one of my favorite plays in football occurs when the offensive team tries to kick a long field goal. From the announcer's build-up of anticipation until the moment the ball is kicked, my eyes are glued to the screen as my stomach turns from nervousness. It amazes me how cool, calm, and collected the kickers seem. Currently, the record for the longest field goal kicked in a game is from 64 yards by Matt Prater. In this video, I will be conducting a further investigation into what it takes to kick a field goal and what forces are used throughout the kick. With Matt Prater's kick, we can use the following system schema. This schema shows that the kicker is making contact with the ball, and the ball is also feeling a gravitational force from the earth. After the ball has been snapped and the placeholder is holding the football is experiencing static friction. This can be defined as the force required to keep an object at rest. Anytime an object wants to be moved, it must overcome this static friction. This force can be applied to Newton's first law, which states that an object will stay at rest unless a force is enacted upon it. Therefore, Matt Prater must apply a force greater than the static force in order to move the ball off the ground. Now, once the ball is in the air, a new force is being enacted onto the ball. This force is drag force. This can be defined as the resistive force acting on an object moving through the air. One of the reasons Matt Prater was able to kick a long field goal was due to the fact that he kicked the field goal in Denver, where the air density is lower due to higher elevation. Additionally, the air temperature was lower than normal. This also leads to a lower air density. Applying both of these factors leads to lower overall drag force acting on the ball in the air, which allows it to maintain its velocity until it is stopped. Now let's take a look at the mathematics behind the kick. The average velocity of the kick was determined by the change in distance over the change in time. This was found to be 17.01 meters per second. The average acceleration of the was found to be the change in velocity over the change in time, which was found to be around 4.94 meters per second squared. The force applied to the ball while it's on the ground was determined as follows. F net of x equals Fg plus Fa. F net x equals ma. Therefore, ma equals mg times force applied in the x direction. We could have found this acceleration in the x direction by using sine 44.7 degrees and by changing the axis as seen in the picture. The static friction being applied onto the ball can be determined as follows. F of s equals the constant of static friction times force normal. The constant was found to be 0.6, and force normal was found to be 0.43 times 9.8. This gives us a static friction force of 2.52. This force is less than the force applied onto the ball, therefore the kicker is able to apply enough force in order to move the ball. The forces acting on the ball as is in the air can be determined as follows. F net x equals negative force drag minus force of gravity equals mass times acceleration in the x direction. The force of drag was found to be negative 2.27, force of gravity was found to be negative 2.96. This gives us an acceleration in the x direction of a negative 12.16. We can take the acceleration in the x direction of negative 12.16 and multiply it by the mass of the ball. This would give us an F net of x of negative 5.2. The reason force is negative in this case is because air resistance and gravity are enacting on the ball in order to slow it down to its final resting point. In the end, it is impressive to compare all the forces that go into kicking a record-breaking field goal.